Hello, welcome back to the first lesson of the semester. We're going to start this unit by talking about something called a random variable. We did talk a tiny little bit about it in class, so hopefully you have some clue. But these are random variables, probability models. We're going to talk about how to represent probability distribution for a discrete random variable, and then how to calculate and interpret parameters about the discrete random variable. So let's go ahead and get started. So we're going to start with a problem where we are kind of creating a discrete random variable or a probability model based on a certain probability situation. So this will use kind of a little bit of what we learned at the end of last semester. So the Podunk Polar Bears, which is a baseball team, have 2 games left in their season. If they win the first game, they have a 70% chance of winning the second game. Otherwise, they only have a 5% chance of winning the second game, right? If you lose the first one, you kind of lose your motivation, lose your momentum, perhaps. So experts estimate that the team has a 60% chance of winning the first game. So we're going to calculate a probability model for the number of games of the remaining 2 games that they will win. So a probability model is basically kind of a table like this one, where I have my numerical variable that I'm dealing with on the top row. That's why we call it a discrete random variable, because there are only specific numerical options. It's not like continuous where it can be anything. And then on the bottom row is the probability of each of those things happening. So in this case, of the remaining 2 games, on the top row, they could win 2 games. They could win both. They could win 1 game, right, the first one or the second one. They could also win 0 games. So when we set up our table, we're putting what are the options for that numerical variable on the top row. And then on the bottom row, we're putting what's the probability of each of those options. Now, in order to find those probabilities, we may need to set up a tree diagram to help us calculate those probabilities. So let's do that. So let's say I have this tree diagram. The first thing that happens is they play the first game. There's a 60% chance that they win the first game, according to the problem. But they could also lose the first game. So if 0.6 is win, then 0.4 is lose. After they play the first game, they're going to play the second game, which they're going to either win or lose. Probability that they win the second game. If they've won the first, they said that that was a 70% chance, so I'll put that there, which means there's a 0.3 chance of losing the second game when they won the first. And then if they lose the first game, they only had a 5% chance of winning the second game, which means a 95% chance of losing. To actually fill in the numbers on the table, though, I need these and probabilities, right? Because the and is basically what's going to get us to that total number of games they've won. If they win the first and win the second, they've won 2 games. So we need those and probabilities in order to fill in our table. So let's go ahead and do that, right? So if they win the first and win the second, 0.6 times 0.7 is 0.42. Win the first and lose the second, 0.6 times 0.3 is 0.18. Lose the first and win the second, 0.4 times 0.05 is 0.02. And then lose the first and lose the second would be 0.4 times 0.95, which is 0.38. So when I think about those numbers, again, my goal is to take these numbers and put them into the table. So my table has number of games won. So I'm not necessarily going to just transfer these in there exactly as we see, at least not completely. So when I think about number of games won, well, one of the options was that they win 0 games. So 0 games would mean that they lose the first and lose the second. So that probability would be 0.38. Another of our options in our table was that they win 2 games. So that the only way that can happen is they win the first and win the second. So that's going to be 0.42. The other option was that they win 1 game. Well, that can happen 2 different ways. They can win the first and lose the second, or they can lose the first and win the second. So that probability is going to be those 2 things added together. So when I do that, I can fill in this table. 0.38 was the probability that they lose both games, so they win 0. 0.42 was the probability that they win both games. So that means they win 2 games. And then the other 2, the 0.18 plus the 0.02, will give me the probability that they win 1 game. Because again, there were 2 different ways of that happening. They either win the first and lose the second, or they lose the first and win the second. So we had to add those 2 together. Right. Another thing to note and remember is that our probability models should always be adding up to 1, because these should be representing all of the things that can happen in this situation. So another way we could do it, if you figured out the 0 and then figured out the 2 and you're pretty confident that those are correct, is I could just add those up and subtract from 1, and that should give me what goes in that middle one. Sometimes that's a good way of kind of getting through it a little bit quicker to keep you from having to do quite as much work when all you're doing at this point is just setting up the model. So let's do another example. Oops. I feel like I skipped an example. Hold on. Pause. Okay, so let's look at another example. And in this example, so now we're going to look at an example where we are given, we're not given it yet, but where you are given a probability model and we want to find some information from it. So in this example, this is about a disability insurance situation. So insurance programs are built based on a lot of different factors. And so this is going to be a very, very, very simplified version of an insurance policy. But just so that we kind of get an idea of where these things come from. So policy holder outcomes. This means for someone who has this disability insurance policy, these are kind of the options of things that could happen on this particular policy. So they could end up needing long-term disability support. They could need short-term disability support, or they could need neither. So long-term would be something that if something happens to them where they can't work for a really long period of time or potentially indefinitely. And then short term means something that's happening on a shorter term basis, so where they don't need as much support. And then neither means there's no disability, so nothing happens. So X is going to be, in this case, the amount of payout, meaning this is what the insurance company is going to pay them in support for that disability. So in this example, or in this policy, the long-term payout amount is $10,000. The short-term payout amount is $5,000. And then if they don't have any kind of disability, then they're obviously going to get $0 from the insurance company. So that would be our actual variable that we are looking at, is the amount of payout that each person gets. Now the probability of each thing happening. So in this policy or in this program, the insurance company estimates that really only 0.001 or 0.1% of people with this policy are going to end up needing that long-term disability payout. And then probability of short term, they estimate as 0.002, which means that the probability that neither of those things happens is 0.997. So this would be what we're given. Here's this information. So there are several things that we can do with a probability model that would help us figure some stuff out about this situation. And one of those things is the average. Now, up to now, when we find the average, you just I'm going to add them all up, divide by the total. But in this case, adding together 10,000 plus 5,000 plus 0 and then dividing by 3 is really not representing the situation like it should be, because some of those options numerically are a lot more likely than others. So what we're finding actually is what we call kind of a weighted average, taking into account the probability or the likelihood of each thing happening. And kind of think of it as if I were dealing with 1,000 people, 997 of them would get $0. 2 of them would get $5,000 and 1 of them would get $10,000. So the average payout per person is not going to be just as simple as adding them up and dividing by 3. I have to realize that some of them are going to happen way more often than others. So my official formula for mean, and we'll also talk about standard deviation. This is our formula chart for statistics, which is in the resources folder in Schoology. But this is where we have some probability stuff. These top 2 are ones that we've talked about already. So in this little table, we see discrete random variable. They give us a formula for mean and then a formula for standard deviation. And they look kind of complicated, got some symbols in there, but they're really not as bad as they look. So let's use them. So here's our little table. We're going to start by finding the mean. So my formula for mean from that formula chart, it says E of X because another word that we will see often used to mean the same thing as mean is the expected value. So in other words, like what can the insurance company expect to pay out per person on this insurance policy? So our formula says we're going to do the sum of X times P of X. In other words, I'm going to go to my table and I'm going to look at each option. I'm going to multiply the X, so the number, times the P of X, the probability, I'm going to do that for each option in my table, and then I'm going to add them all together. So the summation of each x times each p of x. So in this case, that would look like this. So 10,000 times 0.001 plus 5,000 times 0.002 plus 0 was our last option numerically, times 0.997. I do a little math, pull out my calculator, and that comes out to 20. So in other words, on average, the insurance company can expect to pay out $20 per person. Does that mean every single person who has an insurance policy is going to get $20? No, that's not how that works. When you buy an insurance policy, they don't turn around and just give you $20. But on average, so again, if 1,000 people buy this insurance policy, right, again, about 997 of them are going to get 0. 2 of them are going to get $5,000. 1 of them is going to get $10,000. So if I find that average, right, per person, it's about $20. Now that's, again, numerically, that's theoretically, and we'll kind of talk about the difference. This isn't necessarily absolutely going to happen. It's based on probability, but this is what they can expect. So for our standard deviation formula, which looks like this, I apparently didn't do the transitioning correctly, so we can see all of it at once. Our standard deviation formula is definitely a little bit more complicated. So a standard deviation from that formula chart says square root of, and all of the square root is over this entire thing, the summation of x minus mu is the mean, squared times the probability. So in other words, for each of our options, we're going to do the number, the x, minus the mean. In other words, figure out how far away that value is from the mean, square that distance, and then multiply times the probability. So for that first option, it's 10,000 minus 20 is our mean, squared times 0.001. I do that for each option. So 5,000 minus 20 squared times 0.002. And then 0 is our third option, minus 20 squared times 0.997. I add those all together. Right? When I add those all together, remember we squared some stuff, so we kind of have to undo the squared. So at the very end, after we add them all together, we square root it, which gives me my final standard deviation. So adding those all together, that 149,600 is with all of them squared, and then I square root that to get 386.78, which is our standard deviation. As a little extra vocabulary, before we square rooted it, when I left it squared, that is the variance. And the variance is a very important thing that we will talk more about in the coming days. It's one of those things that we don't always use it, but a lot of times it can make your life a little easier. It's kind of a midway step. So 386.78 is my standard deviation. Basically, standard deviation means this is the average distance from the mean. So the average amount of payout per person is $20, but the typical difference from the mean to each payout, the average distance from the mean to each payout is 386.78. So that's telling us that these values are going to be very, very, very spread apart. So while $20 is the mean, we have a really large amount of variation in our numbers and our payouts, which means it's very uncertain, which makes sense because, again, 1 person out of 1,000 is getting $10,000, 2 people out of 1,000 are getting $5,000, and the rest are getting nothing. So there's a lot of variation, which is what our standard deviation is telling us. It's the average distance from the mean. So one thing that we want to think about, and one thing that your insurance companies are going to think about, is how much would they charge for this insurance company or for this insurance policy? How much would the policyholder have to pay to get this policy as insurance? So the mean, the average payout was $20 with a standard deviation of 386. So in theory, right, a lot of ways we can think about this, but in theory, if they want to make money, which an insurance company, they want to make money, we could talk about how much money they want to make, how much are they in it for the money, and how much are they in it for like helping people. But they're a business. They want to make a profit. They have people to pay who work for them. So in theory, they want to make money. So they're going to definitely charge over $20 so that their average payout will be less than what they're making. But with that big of a standard deviation, right, they're going to want to cover their butt and make sure that if something weird happens, if my probability doesn't work out perfectly, they still want to be making money in the end. So they're probably going to charge much more than $20 because that standard deviation is very, very, very large. All right, let's look at another example of finding mean and standard deviation just to drive it home once more. So in this example, we're going to talk about a fake AP class called AP Comic Design. And this is the score distribution on the AP Comic Design exam one year. So we have our 5 options as scores, 5, 4, 3, 2, and 1, just like any AP exam. And then on the bottom row, we have the probability of each thing happening. And this is based on, in theory, it's not real, but this would be based on kind of the global results on this test. So if I wanted to find the mean and standard deviation of those scores, so I wanted to know what's the average score on this exam, and then what's the standard deviation, what's the typical difference from the average score. So to find my mean, remember our formula is we do each numerical value times its probability. We do that for each option, and then we add them all together. So I kind of showed that work here, did a little ... in the middle. By the way, doing something like this on an AP exam is appropriate if it's something that's really long formula-wise and you don't want to write all of it out, but you still have to show your work to show that you understand what the formula is. This is one way to do it. Kind of do the first option, maybe the second, do a little ... and then do the last option. Right? So 5 times 0.24, 4 times 0.24, 3 times 0.27, 2 times 0.08, 1 times 0.01, add those all together, we get 3.78. So that is the average score on this exam. We added up everyone's scores and divided by however many people there were, we should get about 3.78. So then standard deviation, I'm a little square root. The square root's not going over everything, but pretend it is. For standard deviation, I take each option, subtract the mean to find the difference, square that difference, and then multiply times the probability. So again, I showed that work, putting a little ... in the middle because it would have been a lot of numbers. Do all that math in my calculator. All right, when I add all those numbers together, I get 0.8716. Remember that number before I square root it is called the variance. You may be asked about variance occasionally, but then I square root it to get back down to the standard deviation, which is 0.93. So that is the average distance from the mean score. So my mean is 3.78, but on average, right, scores can differ by almost a point. So it's kind of like give or take is what's typical. Okay. I'm going to talk through calculator tricks in class. I will kind of show you my calculator and give you more examples if you want this, but on your calculator, I'm just going to leave this here. This would be how you use your calculator to find these values quicker. But I'm going to talk about this more in class, but I'll just leave this here for a second if you want to pause the video and then try it on your own calculator with maybe that last example, just so you can play with how to do this on the calculator. But I'm going to talk about this in class. Right? Calculator tricks are really good for quickly getting to an answer. You do still have to show your work. All right, I'm going to move on. For our last example, we're going to do one where we create a probability model or a random variable and then talk about mean and standard deviation. So let's say we roll a die. This is a game. We roll a die. If it comes up 6, we win $100. That seems nice. But if not, I get to roll one more time. And if I get a 6 the second time I roll, I win $50. And if I don't get a 6 the second time, I lose. I'm done. No more rolling dice. I win $0. So we're going to create a probability model for the amount of money that we could win at this game. So again, the probability model, the variable I'm doing is the amount of money won. So it's not the number of times I roll 6. It's how much money did I win. So I always want to pay attention to what my variable actually is, because that's going to tell me what number needs to go in the top row. So in this example, I could win $100, I could win $50, or I could win $0. Now in terms of finding the probability here, you can still do a tree diagram if that helps you organize your information, but we can also kind of figure out based on this what the numbers are. So I'm actually going to start with the $100. I think I have the transitions going in a different order. But the $100, the way I win $100 is by rolling a 6. I'm rolling it one time, and I roll a 6. So I just have to think about what's the probability of rolling a 6. Well, on a regular fair 6-sided dice, there's 1 6 out of 6 sides total. So that $100 would be 1 out of 6. Easy cheesy. To win $50, I'm having to roll the dice twice. The only way to win $50 is to roll the dice twice. I don't get a 6 on the first roll, and I get a 6 on the second roll. So 5 out of 6, there's 5 sides that aren't a 6 out of 6 sides total. So 5 out of 6 times 1 out of 6. So I don't get a 6 on the first roll, 5 out of 6, and I do get a 6 on the second roll, 1 out of 6. So 5 out of 6 times 1 out of 6 would be 5 out of 36. And then the way I win $0 is I never roll a 6. I roll it twice, and I don't roll a 6 either time. So 5 out of 6 times 5 out of 6, which is 25 out of 36. Again, my numbers, my probabilities should add to 1. If they don't add to 1, you did something wrong. These do. And then I could find the mean and standard deviation of that variable, basically finding what is the average amount of money that I could win by playing this game one time. So again, the average of the mean would be 0 times 25 out of 36 plus 50 times 5 out of 36 plus 100 times 1/6. I'm going to get 2361. Standard deviation, I would do square root of 0 minus 2361 squared times 25 out of 36 plus 50 minus 2361 squared times 5 out of 36 plus 100 minus 2361 squared times 1 out of 6. When I add those all together, I would get the variance. And then when I square root that, I'm going to get my standard deviation, which is $38.16. And again, you can use your calculator shortcut. Just know that if it's a free response question, you do still need to show the work with the formula. If it's a multiple choice question, you don't need to show it. Use your calculator. So again, we will review the calculator trick in class next time, but that is our first lesson. Okay. Have fun, guys. See you next time.